Magnetic character of substances, atoms, molecules or ions. From magnetic point of view, substances are mainly classified into following two categories: A. Paramagnetic, B. Dimagnetic. Let us first of all understand the origin of magnetic character. It is because an electron in an atom can be considered as a charged sphere rotating about an axis passing through its center. Such a spinning charge produces a magnetic field. This means a unpaired electron behaves like a tiny bar magnet with north and south magnetic poles. Only two orientations of the spin are allowed with respect to the direction of external field. These orientations are clockwise and anti or counterclockwise, as we have seen in the study of spin quantum number ms equal to plus minus 1 upon 2. Well, the two opposite directions of spin produce oppositely directed magnetic fields, so that if two electrons are coupled with anti-parallel spins as they are in a filled orbital, their magnetic fields effectively cancel each other. Such substances are called dimagnetic. Therefore, all atoms, ions or molecules which do not have any unpaired electron or electrons are called dimagnetic. Practically, such substances experience repulsion in an external magnetic field. Examples of ordinary dimagnetic substances are chalk, cloth, wood, etc. On the other hand, substances whose atoms, ions or molecules have unpaired electron or electrons are called paramagnetic. These substances experience attraction in an external magnetic field. More are the unpaired electrons, more is the attraction. Most paramagnetic materials, like oxygen gas, lose their magnetism when they are withdrawn from a magnetic field. But some substances, like magnetite Fe2O3, retain their magnetism and are called ferromagnetic substances. A practical distinction between paramagnetic and dimagnetic substances can be made with the help of a magnetic balance, as shown below. In this balance, the sample of the substance is first weighed with electromagnet turned off. Then electromagnet is turned on and the sample is again weighed. If the substance is paramagnetic, the sample is attracted down in the magnetic field and hence it shows an increase in its weight. Dimagnetic will show a decrease in the weight due to repulsion from the electromagnet. Another common distinction between paramagnetic and dimagnetic substances is that former are usually, not as a matter of rule, colored and latter are colorless. For example, sodium ions are colorless, but cupric ions are colored. The paramagnetic moment of an atom or ion or molecule is given by the following formula. Paramagnetic moment is equal to under root n into n plus 2 Bohr magneton, where n means number of unpaired electrons in an atom or ion or molecule of the substance. Bohr magneton is a unit for expressing this moment. In CGS system, 1 Bohr magneton is equal to EH upon 4 pi mc, where E means charge of electron, that is 4.8 into 10 to the power 10 ESU. H is Planck's constant, that is 6.6 into 10 to the power minus 27 arc second. M is mass of the electron, which is 9.1 into 10 to the power minus 28 grams. And C is velocity of light, that is 3 into 10 to the power 10 centimeter per second. Let us calculate paramagnetic moment for some atoms. For example, manganese Z equal to 25, cobalt Z equal to 27, and nickel Z equal to 28. So let us begin with manganese Z equal to 25. Its configuration is 1s2, 2s2p6, 3s2p6 d5, 4s2. We see that orbitals from 1s to 3p are filled, and the 4s is also filled. There are 5 unpaired electrons in the 5d orbitals of this atom. Therefore, n is equal to 5. Hence, paramagnetic moment will be equal to under root 5 into 5 plus 2, that's equal to under root 35 Bohr magneton. Cobalt Z equal to 27. Its configuration is 1s2, 2s2p6, 3s2p6, d7 and 4s2. It's clear from this that there are 3 unpaired electrons in this atom. Therefore, n is equal to 3. Hence, paramagnetic moment will be equal to under root 3 into 3 plus 2, that is under root 15 Bohr magneton. Next is nickel Z equal to 28 with the configuration 1s2, 2s2p6, 3s2p6 d8, 4s2. It's clear from this configuration that this atom has 2 unpaired electrons. Therefore, n equal to 2. Hence, paramagnetic moment is equal to under root 2 into 2 plus 2, that amounts to under root 8 Bohr magneton. Such paramagnetic moment, which we have just calculated for some atoms, is also known as paramagnetic moment spin only, because this arises due to free spin of unpaired electron or electrons. There is yet another component of paramagnetic moment also, which is known as orbital paramagnetic moment, mu L, such that mu L is equal to under root L into L plus 1 Bohr magneton, where L is equal to azimuthal quantum number of the subshell in which unpaired electron or electrons is or are present.